Share screen? How to do it? Oh, okay. Sorry, I'm so new to this one. So, okay. So let's talk about the loss function. Sorry to introduce you like the math early this morning. So let's talk about the mass function. As we denote this one as data x. So this is the distribution of data. It can be any data set, it can be alias, fashion alias, catalog, and image. So distribution x, we call it P data. So it's just like the data point x drawn from distribution P data. And this one for the fifth one is going to be distribution z drawn from z. It's just like denotation so that you can understand the formula. So let's start with the discriminator. The discriminator, what they're gonna do is like adjust your x with a parameter theta, right? When you do the back propagation, you adjust the parameter of the discriminator theta, and the output will be the x. And for the generator, it will adjust your z by another theta. And the output will be gz. After passing through the discriminator, this will produce you another output of b, g, z. This is the thing that we just talked about earlier, right? So what I want you to remember right here is to understand what is P data x. P data x is like the real image. PZZ is the fake image. What is dx? Dx is the output of the real image passing through discriminator. What is dgz? Is the output of the fake image after generator passing through discriminator. Okay, that's the notation. So let's start the binary cross entropy formula. Okay, so so the loss function, so this is the cross entropy. The loss function of y and y hat is y hat right? So this one is the cross entropy loss function. You may recall in week 5 or week 6. And because the first one, we're going into calculate the loss of the real image passing through the discriminator. Let's focus on that first. So our y, what is the label for the real image passing through the discriminator? Everybody remember? Anybody remember that? What is the label? Yes, it's 1. And the output of the real image passing through discriminator, what is the output? It's dx, right? But on both, right? The real image passing through discriminator produce a dx output. So we have y hat dx. So when you replace y hat into the loss function, we're going to have a real loss. Right? 1 here and here. And we have block of logarithm of dx. Let's calculate the fake one. What is the label for the fake image passing through discriminator? 0. And what is the y hat? Yes, it's d, g, g. So can anybody help me calculate the fake discriminator loss by given like 0 and dg? So this one is going to disappear, right? Because it's 0. Anything left is 1 minus for 0 is 1. So we only have like logarithm of 1 minus d. So we have this real discriminated loss and fake discriminated loss. So what is our intention to do with that? How can we optimize that? So the real discriminator loss, it tells you how much a real image is a real image, and you want to maximize it, right? For discriminator, because you want to distinguish the picture. So you want to maximize this thing. For the fake, it's the same thing. They want to categorize the fake image as the fake image, which means like label 0. So you also want to maximize the ability of distinguish the fake image. So we also maximize this one. Let's say, so for the first one, because this one is really long, so I will call it A. This one is B. So we have the graph. The first function right here is dx. And as we already mentioned earlier, dx will range from 0 to 1, right? From 0 to 1 right here. And it's only range in this area. So we're not talking about this area. So what is the maximum value of when we're gonna have the maximum value of logarithm of dx based on this graph? It's when dx is 1, right? It's right here. We have the maximum value of y. And this one, the graph function of it is like this. This one is D, G. So when do we have the maximum value of this? When the GZ is 0, right? Which it makes total sense because this one is for the real image and we really want the dx to close to 1, which is labeled the real image. And this one, we really want the dgz to have label 0, which is the label of the fake image. So by summing up this function, you can look at this here. I need to right? You can see it here. For the discriminator loss, their intention is to maximize the ability of distinguish the real image and maximize the ability of distinguish the fake image. So this is the loss function that you have for the discriminator. So the next one is the generator. The purpose of the generator is trying to fool the discriminator. This produces a fake image, but it's want the discriminator to guess it as a real image, right? So can you tell me when it's going to happen right here? It's like when DGZ approach 1 right here, the loss will like becoming really, really small. So it means that you want to minimize this one to a really, really like minus infinity so that the discriminator will guess your picture as the real, which is labeled 1, right? So that's why we have the loss function for the generator as the minimize of this one, the ability to distinguish a fake image. Everybody got it? I think it's clear. Yeah. Okay, so yeah, that's it for the loss function of the game. This one is the summarize of it. This means that you try to maximize the loss function of the discriminator and you try to minimize the loss function of the generator given by the ability of distinguish the real image and the ability of distinguish the fake image. So that's how we come up with the loss function of the game. So yeah, so now it's just a theory. So when you come into a TensorFlow and try to implement it, we have do the same thing. We will calculate the discriminator loss by 2 components, the real discriminator loss and the fake discriminator loss by comparing each one to an array of 1 and an array of 0, which represents for the fake of the real and the fake. Okay, so that's it for the math. Now let's get to see like how like GAN look like in application. So I always talk about the GAN like a family because like I like the way that they have like name each of the GAN application by the new name. For example, DC GAN, cycle GAN, tension GAN. It's like you join an Asian family, you get a lot of relative. So, okay. The first one I want to talk about, and also we're going to have a lab section on this GAN because it's so fundamental. This is the first GAN application. It's about generate image, any image. And what you see on the screen is the generation of MNIST. So as you can see at the beginning, it's really noisy, right? You cannot distinguish which one is number. But at the end, they successfully produce a new number look like this. And take it from that, they step into generate new faces. Like imagine that you see a face that the computer can generate a face that look like nobody on the earth. It's completely new. And at the beginning, it's not garbage. It's not look like horror story. In 2015, it's like it's really but it's get better, better, and better all the time. And this is the state of the art. In 2017, using progressive GAN, they successfully produced a 1024 by 1024 image of face. Can you believe like no one in this actually exists? It's just AI. Yeah. And I want to show you a video on that. Can you turn off the light? So I talk about a lot of math, so I found a really good way, a really good video to visualize how can they, what? How can they make like how machine can make face? So I really want to show you guys this video. Okay.
Just click here and skip to the results. Alright, so let's talk about autoencoders. An autoencoder is simply a transformation that tries to map samples from one space into the same space. So you might be asking yourself, why is that useful? I don't see how that's different from an identity. The idea is to try to squeeze the high-dimensional space through a lower-dimensional bottleneck to see how well it can reconstruct the original samples. In this case, there's an encoder and a decoder network, which you can think of as black boxes that do the complicated math for you. With images, it's a lot like JPEG compression. You can afford to lose a lot of the dimensionality, which is the file size, but still reconstruct the original, with only a small loss of quality. Let's look at the JPEG example. You probably can't even see the quality loss, but this is already compressed 14 times smaller than the raw original size. But watch what happens as we decrease the dimensionality. The quality has suffered, but it's still recognizable. So let's compare that to the autoencoder we're about to use. We're starting with an image that's 144 pixels wide by 192 pixels tall with 3 color channels. That's about 83,000 dimensions. And we're going to squeeze that down through just 80. That's more than 1,000 times compression. But how can we possibly expect a decent looking face with this much reduction? We just saw what happened to JPEG with 100x compression. The reason is that JPEG has to compress all possible images, whereas we're only interested in faces. If you think about it, the space of all possible faces is way smaller than the space of all images, by orders of magnitude, especially considering they were all posed similarly.
It's like an easy
Since
task.
we force it to learn only 80 features, the only way to provide a good reconstruction, given what we just saw with the general compression, is if those 80 features are face-specific. So hopefully we'll learn what it means to be a face. There's one other.
So the first intention is that we trying to map all the feature of the face by a latent space or an embedding. So 80 dimension will describe 80 feature of your face.
The trick we can use to simplify this model, though. Since we really just want to generate faces, we don't actually need the encoder, not even during training. Instead, we just embed all trained samples randomly into the latent space. Their weights then just get updated just like the network weight for training. To generate a random face, we'll just sample each of the 80 dimensions using the same means and variances as we see in the training. So what 80 features do you think I've learned? Well, let's see. Each of these sliders represents one of the 80 latent space dimensions. Each tick mark is one standard deviation, and the center is the mean. You can see that each slider is making a change, but it's not clear what each one does. And in fact, what the slider does actually depends on the state of all the other sliders. So it's really impossible to say. So does that mean we just learned some insanely complex representation that humans could never comprehend? Are we done? Well, no, there's actually a big mistake we made, and fixing it will help us solve this problem and improve the face quality. What
Okay, so I'm gonna skip this one, but it's the main idea is like, do you remember the PCA, the elbow? So 80 dimensions to describe a face. So mostly like the first 20 or the first 30% of the dimension will describe almost 80% of the image. Remember the elbow, the curve? Like this. So a lot of face feature is already in the first 20%, 21st features. And the next 20 to 80 will to describe like small feature of your face. Can anybody guess like, so what is the feature that is in that 80 dimensions? Let's say you have like a photo of a lot of people. So what do you think? Maybe one dimension is about, is it a male or female? Right?
The vast majority of the variance is actually only in the first 20 or so dimensions. Then we'll update our face generation as follows. We'll generate a sample in the PCA distribution, convert the smallest.
Okay, let's test it.
So let's check it out. I've sorted the sliders from largest to smallest principal component. So the number one most important feature is apparently shirt color. I guess it makes sense. The shirt takes up about a third of the image, and it can range from pitch black to completely white. Number two appears to be gender. Obviously, hair length is highly correlated to gender, and long hair takes up a lot of the image. Number three is head position. People tend to lean their head during photos, and it's not too surprising that this would be a dominant feature. Number four is the person's height. Again, not too surprising. It varies a lot between people. Number five is a little weird. I call it hair density. It's kind of like how much the hairline recedes, and also how light or dark the hair is. Number six is head size, or more likely how close or zoomed in the person's head was to the camera. Number seven is collar height, not one I would have thought of, but I guess it makes sense. Okay, so it's just go on. So the main idea is like when you input an image, it's gonna reduce it into the embedding that contains a very like important features of your data, and from that feature, it's gonna upsampling into the face. I hate beautiful AI. And another fun application is like generate anime character. All of these characters not real. Of course, they're not real. Like they haven't been drawn before. But like the idea of this is to like, you know, for anime illustrator, they have to spend a lot of time to draw like minor character. It's like people in the crowd, people in the game, in the crowd, so they don't want to do it. So this one gonna help them to produce new character. And the next dimension of GAN, the next application is about pix to pix. If you're interested in changing one photo into another one, this one, you may take a look at it. The first one is like, if you input a segmentation image of the street, they can give you back the real street, or give you a satellite image. It can give you the map. It can draw the map for you. Or this one, we're going to have a lab section on this afternoon. It's like you give them a layout of the facade of your house. It's gonna draw you a house. It's gonna complete that. And the next one is black and white image into color, day to night, night to day, and also like from edge to photo. So let's take a look how they do it. As we just mentioned in the face, when you input, this one is a model to colorize an image. You input a grayscale image of 256 by 256, and then it will extract the feature
until this point is an embedding of 4x4 that contain all the important feature of the input image. And then after that, using upsampling layer, we're going to talk about it later, they're gonna give it back like this, and your output will be 256, but in 3 dimensions, which is RGB. It's like a unit. Using the same thing, if you combine different embedding vector, you can get surprising output. For example, if you use man with glasses minus man without glasses and plus woman without glasses, it's give you back woman with glasses. It's more like a panda. Something like this. It's really cool about the idea how to use embedding to create image. One subset really famous of pix-to-pix is the cycle gain. Cycle gain can be said like you apply the texture or a characteristic of one other photo onto another. For example, from a normal horse, you change it to a zebra. It's running around in the video. Another one is to change a painting into a real photo and vice versa. I'm going to talk this to anh Huỳnh, but he's absent, sad. This one is used for automatically drive car. So they can change a sunny day into a rainy night or from a rainy night into a sunny day. So you can, so the car can see the street better. Let's take a look at it. This one is a research of UC Berkeley. What I want to show you, I want to show you this one. Let's look at it. From a night street, they change to the day street. From the day street, they change to the night street. Yeah, to support the car. This is the team to make a cycle game. The team who invented the cycle game. It's funny. Ah, I hate beautiful AI. It's really cool, right? To see the ability like that, you can change the image into whatever you want. And even step further from that, from the cycle game, just to change like normal image to support like car and stuff, we step into cycle game for deepfake. So imagine that one day you go into the internet and you see your face in video that you have never been in the video. This is what going to be. And actually there's some like legal case about like people put stranger face into porn. Like one day you're gonna see your face in the porn. And let's take a look at the documentary about it.
We're entering an era in which our enemies can make it look like anyone has signed anything at any point in time.
Jordan Peele created this fake video of President Obama to demonstrate how easy it is to put words in someone else's mouth.
Moving forward, we need
The Obama video is not right. It's not real.
Not everyone bought it, but the technology behind such frauds is rapidly improving, even as worries increase about their potential for harm. This is your Bloomberg quick take on deepfakes. Deepfakes, or realistic-looking fake videos and audio, gained popularity as a means of adding famous actresses into porn scenes. Despite bans on major websites, they remain easy to make and find. They're named for the deep learning artificial intelligence algorithms that make it possible. Input real audio or video of a specific person, the more the better, and the software tries to recognize patterns in speech and movement. Introduce a new element like someone else's face or voice, and a deepfake is born.
It's actually extremely easy to make one of these things. There were just some supposed breakthroughs from academic researchers who worked with this particular kind of machine learning in the past few weeks, which would...
It's pretty crazy, right? From like the first idea is used on making a horse into a zebra, and now it's making me into Donald Trump. It's crazy, right? And it all start with just the simple idea of cycle game and the model that you just say. And the next one I'm going to talk about is, I love this one because when I was a designer, there's a task I really hate, is to edit photo. Geez, like you have to erase certain object out of the photo, and it took days, especially for the hair. For the objects that overlap each other, it's so hard to do it. But there's a GAN on image indenting. This can help you to patch the image and like remove the stuff that you don't want inside the image. Let's look at the first one. Is fairly easy. Let's just remove like a human here. This is the output. It's still easy. Yeah. Let's see the hard one on human face. Just new eyes. And which look natural. Now let's come to the hair. He lost a lot of hair. That's the eyebrow. Now he's getting younger. Of course, you can do that kind of stuff with Photoshop, but I guarantee you, it's gonna take you like half a day to really give a look of a human like natural. But for GAN, you just train the model and you do the things very easy. That's such a revolution in the way we design.
But I still don't have like complete control over like how it should look at the end, right? Like they replace it, but I don't really know how it's gonna look at the end, right?
Yeah.
It's like for this, for example, I think they trained on a celebrity data set, right?
At a face data set.
And the celebrity data set was really extensive, so they had a lot more women than men. So like all the eyes they put in are all female eyes.
Yeah, there's a risk for that. Yeah. But at the same time, remember when we do the face, there's like 80 dimension. You can turn it into a slider. Maybe like if you want to develop that software that you can use the slider to assist that, this may be a good idea, right? So the next one I want to talk about, like, I'm not going deep into this, but it's one of the most advanced GAN because it's hard. It's like you input a sentence and give you back the image. For example, this bird is completely red with black wings and pointy beak. Back or beak? Beak, yeah. Yeah, and it gives you the output the same with what you have described, which is amazing. And this one is so new. I think it's like 2017, is it?
Well, that's second one, but the second two was I think a few months later, and then they combined with attention again, and now the newest one is from Germany, I think, which is like SOA or something. So then they replace it by like multiple objects. So the newest one is like last year. So
the first idea of this, they use 2 stages. You don't need to understand it. I just want to show you. The first stage is kind of the same with pix to pix. But at the beginning of it, it's used like a kind of like NLP word embedding to understand the context of the word you put in. And from that, it changed into a latent space and use upsampling into the image. That's the stage 1. And the second stage, they try to improve the resolution of the image. Take a look. The first stage is so garbage. You cannot see what actually is it. And after the second stage, right here, everything's become like a lot clearer. That's why like there's a lot step here. But everything is on the main idea of downsampling and upsampling convolutional layer. And I'm gonna talk about it later. Okay, there's something that I wanna show you more. I wanna show you some more application of it. One of the newest thing is like, given a image of the face and you output another angle of the face. This one This one right here is the input photo. And this one is the output photo. Yes. And this one is the real image. And you can see GAN makes such a tremendous victory on this one. See it? Input, output, input, output. And this one can solve the problem of object detection when like your face like moving around. And the second thing is that it's paved the way for the 3D GAN. Because if you can rotate the image, then you can make a 3D object, right? And it's gonna be one of the way we can do like a 3D GAN for human in the future. The second one is you see it on Apple. They released their phone with like can make your face into a Bitmoji. It's very simple, but it creates such a hype for the Apple fan. I don't know why. Age GAN, make you look younger, like this. Blur GAN, deblur image. This is the output. Input, output. Input, output, which is crazy. Yeah. Application for object detection. This is my final project. This is super resolution, low resolution image into high resolution one. Yeah, we talked about deepfake already. Anything else? Oh, is this the 3D? I don't like you talking. So from adjusting the embedding, you can change the chair from has the armchair into the not armchair, or like a car into a boat. But this idea of 3D GAN is fairly new. It's in the 2018, I guess. So the research is just at the beginning. So if you want to step into it, it's the right time to do it. And the most of the object they can do right now is like they work on the furniture object, like the vase, the chair, and table, doing like Lego. But then in the future, it will step up into another like more sophisticated quality image. For example, you see like here, a table with this one have the latent space like this, and you minus this, represented this furniture, and you plus this furniture has the latent space like this. And when you add it up, it's going to have a new table that inherit all the feature from the other one. Yeah. Okay. So, and also music and stuff. Also can use GAN for it, for medical, to detect like tumor. Yes, I haven't read it, so I don't know how to talk about it. But if you're really interested in that, you can take a look into it. Let's take a look into the generator. We talk about the ability of generate image. So what exactly the magic inside the generator that can do it? As I already say, like there's a 100 note latent space embedding or noise right here, and then they up sampling it until 1024 until it's reached the final shape of 64:64:3 as an image. And by doing that, we use convolutional 2D transpose. Before that, there's a lot of other way to do it. For example, like bicubic to restore the image, bicubic, or nearest neighbor, or like upsampling. But the most advanced one right now is the convolutional layer, which called convolutional 2D transpose. So the easy way to describe it is that it's the inverse of the convolutional 2D. So if your convolutional 2D try to, reduce the dimension of the image, this one inverse of that process and make it bigger. For example, right here, you have the input of 0, 1, 2, 3. You have a kernel of 0, 1, 2, 3. And you want to make it into 3, 3 right here. This kernel gonna apply on the first pixel and produce it's like multiple, matrix multiple. 0, 0, 0, slide into the next one, which is 1. So this one, multiple for 1, reduce you 0, 1, 2, and 3, and go on for the next 2 sliders. And the output of it will be the sum of this one. So one thing that you really want to know, and I think it's important to know, is decide the output shape of your convolutional 2D transpose. So actually there's a formula for that, which is given right there. So this is a formula, so don't ask me to explain it because it's a formula. So by using that formula from a input shape, you can calculate the output shape. So let's do it together. So we have O here, you know, for output shape. So let's say right here, kernel or output shape or input shape, we keep everything square. So that's easier for us to calculate. And also, I think it's like a common practice for convolutional view, to do convolutional layer. Output shape will be stride, how the kernel slide through the input, stride, multiple for the input shape, minus 1 plus the kernel size. For example, this is 3. So it's 3. And you plus, you minus for 2p. 2p is like 2 times of the pattern. So let's apply it. For example, let's try this one. So from a 2, we try to convolutional transpose it into a 4. So it's 2, right? So the stride is 1. The input is 2, 1, plus the k is the kernel size is 3, right? And there's no pattern. So the output will be 1, 1. So this is your output 4 by 4, right? So can anyone help me to do the next one? First of all, let's say you don't know, you haven't seen the output of it yet. So we have the input, the stride of 1, the input of 2, right? Sorry, the input is right here. It's like outside down. 2, 1. What is the kernel size? 3. What is the pattern? I have everything. So 1, 1. Yeah, it should be 4, but it was not right. Oh, oh, okay. Slice 2. Okay, let me look at that later. Let me look at that somewhere. Maybe the visualization is not right. I think it should be the convolution. It's not the convolution. Yeah. Yeah. Okay, let's try the last one. So for convolution 2D, like transpose, when you do the stride, it's gonna, the way they visualize it, they're gonna put like a padding into it for the stride. If the stride is equal to, it's gonna put like 1 not 0. A little bit clean of that, so that it will slide like to make the next pixel. So we have a stride is 2, input is 3, corner size is 3, and the padding on 2. The what? Oh, the padding is 1. So we have 4. Oh, yes. Yep. Yeah, I think 7 for the second one, right? I get it wrong. Let's do it later. Okay, so this is the formula how you can calculate the output shape of your convolution into the code. Sorry for the confusion. But when it comes to like syntax, like for the keras, there's only 2 options for the padding. The first one is this padding same, and the next one is padding valid. For padding same is like you tell the machine like to do, hey, let's do the padding so that the output shape will be equal to the input shape. So that is when the stride equal to 1. But when the stride is not 1, the keras will try to adapt the padding so that the output shape will be the input shape multiple for the stride. That's the formula. So if you use a keras, if the stride is 1, it's going to give you the same shape of the input. If the stride, for example, 2, oh sorry. The output shape will be the input shape multiple for the stride, no matter what your color size is. For example, if you take a look at the DC GAN right here, for the DC GAN, for example, like from 7 to 7 to 14 by 14, you're supposed to use the padding same and the stride too, so that the output size will be double. Yeah, and for the padding valid, they don't care about the padding, so there's no padding. They it's like for the padding same that you want to keep the feature of your image and not losing them. But for the padding valid, it's just like, hey, it's okay to lose some pixel of the image while you're doing the convolution layer. And the shape for the output, we can use the padding valid. It's just like remove the padding because they don't use the padding. So the output will be this. Right? Because the padding was already 0. Okay, everyone's clear? Sorry for the confusion of the convolution layer. Okay, so that's it for this morning. And when I start studying GAN, there's no one taught me about GAN. We didn't teach that in the latest course, but I follow Jonathan Boyd on Medium. He has a really cool, he has a really cool series of GAN from a very basic to very advanced GAN. So if you're really interested in the topic of GAN, I recommend you guys to go from the very basic, what is generator, what's discriminator, to very advanced GAN. Yeah, he has a lot of articles about GAN. It's like a GAN advocate. Yeah, I including the link here. And for the other 4, it's like a fun interactive demo that you can try on. Okay. So thank you for this morning, and I see you this afternoon with the last section. Oh yeah.
So maybe that's not good. How to use it.
How to stop it? Like just click this?
Yeah.